So in this chapter, let us apply the concept of torque and angular momentum for the rigid bodies especially. So the angular momentum about the center of mass of the rigid body is the first context. If you take the rigid body and take its center of mass, with respect to the center of mass, the angular momentum can be given by LC. And this is equal to sum of angular momenta of all particles with respect to center of mass. The particles are discrete, but for rigid body, we cannot distinguish one particle from the other. The particles are continuously arranged. Therefore, instead of ith particle, we can write very small segment of the rigid body. Let the segment has mass dm and that elementary segment is located at a distance of r from the center of mass. So instead of ith particle, you cannot distinguish ith particle from kth particle, from nth particle. So for rigid body, instead of ith particle, let us take the elementary segment and its mass be dm. So mi is equivalent to dm. This segment is very, very small. It behaves as a point mass. So mi, mass of the ith particle, can be written as dm for continuously arranged particle. And vic is, let be v, velocity of this point with respect to the center of mass, let the point be p. So vpc is equal to v, and this is always perpendicular, as I told you, in kinematics of rigid body. And this is rpc, this is equal to r. So vpc is equal to v is equal to r into omega as per the kinematics of rigid body. So instead of ric, this is r. Instead of mi, this is dm. Instead of vic, this is v. And cross product is there. And instead of summation, it will be integration. For a rigid body, the momentum about the center of mass, axis. The axis is passing through the center of mass. So this is equal to integral r cross dm into v. dm into v is the momentum of this point mass or element with respect to the center of mass. D is the velocity of this element with respect to center of mass. And this point moves perpendicular to the line separating these 2 points. So v is the velocity of this point with respect to center of mass. This is always perpendicular to the position vector of the point P with respect to center of mass, that is assumed as r. Since it is perpendicular, omega is equal to this velocity Vpc upon this perpendicular distance rpc as per the definition of the angular velocity relative. Vpc is taken as v and rpc is taken as r. So v is equal to r into omega. R cross dmv vector. This is dmv vector. This is dmv vector r cross. Bring the tails of these two vectors r and dmv vector to a point, and r cross dmv vector, this is pointing in. So we can just write r dmv sine, the angle between these two vectors is 90 degree, and the angle is 90 degree, sine 90 is 1, and the angle is rotating r cross mv. This angle rotates in clockwise sense. Therefore, this is minus kf. R dm v minus kf. Since this is a constant vector, take it out. R dm into v. And v is equal to r into omega. Omega is the angular velocity of the rigid body. Kf r dm. Instead of v, I can write r into omega. Omega is the angular velocity of the rigid body. Take it out of the integral. Minus omega kf r square dm. Minus omega kf can be written as omega vector r square dm integral. This is the expression for the angular momentum of the rigid body with respect to its center of mass axis. This term r square dm integral is called moment of mass. Mass is multiplied 2 times with the distance. Therefore, this is called second. 2 times it is multiplied. Therefore, it is called second moment of mass. First time it is multiplied, the first moment of inertia or first moment of mass. This is the second moment of mass. Second moment of mass. We can call mass as inertia. Second moment of inertia, or more popularly, it is called moment of inertia, given as I. Moment of inertia about which point or which axis? About the centroidal axis or the axis passing through the center of mass of the system. Therefore, angular momentum about this center of mass axis is equal to, this can be written as I c into omega. Here I c is the moment of inertia of rigid body about center of mass axis. Is given as integral r square dm. R is the distance between the element and the axis. So here the emerging concept is known as moment of inertia. Next context, we will glorify the moment of inertia. We will calculate the moment of inertia of some rigid objects for some time. Before that, let us take an example to understand this concept of angular momentum of the rigid body with respect to its centroidal axis. Let us take an example. Let us take a disk. Let the disk rotate with an angular velocity omega is equal to 2 radian per second. Its mass is 2 kg or 3 kg. Find the angular momentum of the disk about this axis which passes through the center of mass and perpendicular to the plane of the disk. given that moment of inertia about this axis is equal to 5 kg meter square. LC is equal to IC into omega. Omega is given as 2 radian per second. Which direction? Jacob direction. So this is the y-axis. And IC is equal to 5 kg meter square is given. Therefore, LC can be written as 10 kg meter square per second. In which direction? Jacob direction or upward.